Hi everyone. Thank you very much to invite me to this fantastic congress. My name is Hadrien Calmet, and today my talk is about the cough jet dynamics, droplets transport, and inhalability over a 10-minute exposure. I do this work with some colleague from the Barcelona Supercomputing Center, Daniel Mira in Ambrose both. And we do this work in collaboration with Professor Kiao Entavang from MIT, Australia. So you will ask me, why another cough simulation? Because a cough produces a high magnitude of expiratory droplets compared with breathing or talking. And as sneezing is not a symptom of COVID-19, despite it having higher magnitude of expiratory droplet than coughing, it was not considered relevant in this study. Vaccines have short-term efficiency against the early variant of COVID-19. Therefore, it's crucial to assess the risks of disease transmission and also be able to characterize the transport of respiratory pathogen. While many studies apply lower fidelity model, like a rounds with turbulence model, about the cough, the larger dissimulation, even the direct numerical simulation approach, provide greater detail, but are still limited in simulation time due to the computational cost. So here we carry out 10 minutes of cough droplets dispersion. In general, the literature shows that droplets diameter have significant influence with small droplets diameter, let's say less than 5 microns. This is why the evaporation aspect is considered in this study. So the geometry model consists of two humans standing face to face in the room 2 meters apart. So the first human, let's call him Hadrien, produce a cough from the mouth during 1 second with the volume flow rate and the cumulative distribution function of droplet diameter, both based on literature that you can see in the slides. The temperature is set to 34 degrees, while the relative humidity value is 80%. Nasal cavity anatomy is included inside the second human, let's call him Kiao, and the breathing cycle is modeling during 10 minutes. The ambient environmental conditions are set to 23 degrees with a relative humidity of 20%. We also include the body temperature at 34 degrees to account the thermal plume convections. To resolve the spatial and temporal multiscale problem, we apply two different meshes. One for the coughing event, mesh M1, so to resolve the cough jet, then all the features. Then the mesh M2 to resolve the droplet aerosol transport for 10 minutes in the room. Let's notice that without a cone refinement, the mesh M2 allows larger time step, so making the simulation of 10 minutes feasible. So to sum up, the workflow here is a simulation of the cough during 1 second with the mesh M1. Then we interpolate the fluid and the particle data resulted into the mesh M2 to continue the post-cough simulation during 10 minutes. So to resolve this equation, we use the in-house code that we develop here in the Barcelona Supercomputing Center. It's called AIRWAY system. So it's high performance computational mechanic code. Is a multi-physic, multi-scale, is portable to many platforms, and is highly parallel because it was designed from scratch to run on supercomputer. So it's composed by different modules with fluids, solids, electromagnetism, chemistry, heat transfer, Lagrangian particle, and so on. Then you can couple this module, like for example fluids, solids, and Lagrangian, to produce a fluid structure interaction with particle, for example. So to resolve the cough, we use a Eulerian and Lagrangian approach using a large ED simulation, using a turbulence model well. The droplets ejected during the cough event come from various locations and so from various mucosal tissues. The bronchiole with a droplet diameter around 1 micron, the larynx between 1 and 20 micron, and the oral cavity between 20 to 1000 micron. We can observe in this figure the evolution of this classification after 1 second of cough. So the droplet trajectory are shown on the left and the corresponding size distribution on the right. More than 90% of the cloud puff is formed by 0.5 microns droplet diameter and move horizontally and affected by gravity. They will stay in suspension during hours and hours. Then, the medium droplets, which are a mix where some of the trajectory are affected or not by the gravity, and the large one, where all the droplets are falling in the floor, having a ballistic trajectory. On this slide, we can see different views of the thermal puff cloud with diameters under 5 microns diameter. The isosurface of temperature equal to 23.4 degrees. The literature has found that the moving puff cloud is dense and the various pathogens, including COVID-19. Notice that the vortex ring structure goes faster than the bulk of the thermal puff. Now we focus on the vortex ring structure, and we can observe that it is composed by 2 temporal periods, the jet-like and the puff-like, already observed experimentally in the literature. First period, the jet-like is dominated with a high velocity and an important fluid droplet mixture, while the second period, the puff-like, is dominated with low velocity and a high dilution. So we observe a random deviation, consistent also in the literature, possibly due to the asymmetric air stream produced by the exhalation of Kiao. Now let's have a look to the post-cough results. So just to recall, we interpolate velocity field, pressure field, temperature field, and water vapor fraction field from the cough simulation on the mesh M2. Then also, of course, the droplet position and the properties. And we continue the simulation during 10 minutes. The breathing region is defined here as a sphere around the Kiao's nose with a radius of 0.5 meter, representing the tidal volume that Kiao can breathe. Therefore, the data of this region is useful to understand the evolution of the droplet size distribution and thus to be able to model the breathing risk exposure. So now let's see the evolution during 10 minutes. As you can observe, the critical diameter size susceptible to inhalation is 0.5 micron. Even if the number of droplets disappear gradually with time, an accurate analysis of probability distribution is difficult. However, the results of the mean value at each minute stay consistent. In this slide, at the top part, we can see the evolution of the diameter size of the inhalated droplet. So we backtracked the droplets inhalated by Kiao to the exit of Hadrien mouth by monitoring the particle distribution at initial state with a mean value of 2 micron until the final state with a mean value of 0.7 micron. Therefore, these results highlight the importance of the evaporation rate because the diameter affects the aerosol, the aerodynamic of the droplets. Underneath, we can observe the temporal variation of the inhalated droplets deposition with 2 clear slopes. The blue one, which is probably influenced by the trailing puff from the cough, and the red one, which is probably influenced by the dissipated momentum from the cough. So now I would like to show you a very nice animation that I produced with Blender, because now in Blender they have an add-on that you can read and incorporate results from ParaView, and so you will see the rendering is very nice. And after a couple of minutes, I imagine, for the question. So this is the animation. So here you can see the cough event with the 3 different classifications. So with the small droplets, the medium droplets, and the large droplets. So as I said before, there are 3 different locations for the production of droplets. So the small droplets on the bronchiole, the medium in the larynx, and the last in the mouth. So there is 3 different sizes. So here we show only the small one, because the interest is they stay in suspension during hours and hours. So as explained, there is some features like the vortex ring structure. So I do a bullet time. I thought it was quite nice to see the structure of the puff cloud and also the vortex ring structure. So we follow the puff cloud and the vortex ring, and we observe that the vortex ring structure go faster than the bulk. Then also I compare the top view and the front view to have an idea of first the deviation and also the dispersion or the dilution of the thermal plume.